Today we're going to be looking again at some more graphing, and we are straying away from that line graph that we've been working on, and we're going to be looking at some absolute value equation graphs. So I have notes number 8 here. Now, before we write down kind of how we're going to be graphing these, I want to do a little investigation, and so I'm actually going to use Desmos for this. So I'm going to switch when I'm sharing. So you should have the notes in front of you, and I'm kind of using Desmos to go through this investigation because as of right now, we don't know what these absolute value graphs are going to look like. So I'm going to put in here just basic absolute value where I'm looking at the graph here of y equals the absolute value of x. And you can see that it creates this V-shaped graph, okay? And in years past, when you're right in front of me and you have a piece of paper, I talk about this line. So here's a line, y equals x. And you can see that that line, that on this half of that V-shaped graph that we had initially, that my line is lying right on top of it, right? So like the absolute value of 2 is 2. And also if I just use my equation, if x is 2, y is 2. Okay, so that matches. What happens over here is when I take an absolute value of a negative number, it becomes the positive of that number because distance is always positive. So where before on this blue line where it's just y equals x, well, when -2 became -2, when I take the absolute value of -2, it becomes positive. And that's why it turns around in that middle of that V and starts going back up again because those what were negative numbers without the absolute value now become positive y numbers. And that's what's creating kind of that V shape, okay? So overall, we now know that these absolute value graphs will be V-shaped graphs. The first part of the investigation is looking at how that graph changes when I change the number in front of it. So I'm going to, I actually think I'm going to do that last graph. The first graph listed, I'm going to do it last. So I'm going to just write the exact same equation. So I have y equals absolute value of x in there twice. And I'm going to look at the second graph in our notes, which says y equals 1/3 x. So let's see what happens when I add a 1/3 in front of it. Okay, and I'm looking at the green line here. So you can see that adding 1/3 in front of my absolute value, that my graph, the V became wider. Okay, and we could see if I did 1/5, or let's even look at 2/3, still wider. Now, what if I flipped that and did 3 halves, not wider anymore? Okay, that's because that fraction became greater than 1. So what we should be observing there is that a fraction less than 1 in front of my absolute value made the graph wider. The third graph in that investigation is just y equals 3 absolute value of x. And you can see that that took my initial red graph and made it a skinnier in that green graph that's there, okay? Now, the last one I want to look at, so let me switch screens and then we'll look at the last one together. Let me go back to my first screen. So what I looked at is I looked at these two so far. So I looked at y equals 1/3 x and y equals 3x, okay? And what we saw with the 1/3 x is we saw if this was my initial graph, which we saw was just kind of going up by 1 each time, or it had a scale of 2. Okay, here was my initial graph. When I typed in 1/3, the graph got wider. And in fact, it was just like slope, up 1/3, up 1/3, getting wider this way and then going backwards. Same idea on the other side, not quite like slope there. That would really be negative, right? But because we have this V-shaped graph. Okay, and what happened when I put that 1/3 in front of my absolute value sign, that my graph became wider. looking at my original graph. So again, just going up by 1 on both sides. That was what my original graph was. And then when I threw a 3 in front of it, my graph got skinnier. And in fact, we could graph it by going up 3 over 1. That's how much skinnier it had gotten. There's my new graph. Notice it didn't shift this point, right? It was still starting at the origin the way that we have it written in there right now, where we just have absolute value of x. So now let's look and see what happens when we have -3 in front of our absolute value. And so you could maybe predict that it's something similar to here, but what is the negative going to do? So before I go back to Desmos, let's go ahead and draw in our original function again. Okay, so that's just y equals the absolute value of x. And now let's look at my Desmos screen. And let's throw a negative in front of that 3. And what happened? Our graph flipped over, okay? Because what's gonna happen is it's gonna multiply it by a negative every time. And so what had been previously a positive number now becomes the negative of that number. Okay, does that make sense? So it's gonna flip the whole graph up kind of upside down. So on our notes, when we have -3, it's still narrower because of the 3. And it's, so hold on, let me go back. The last one I didn't fill in. So this became more narrow. This is narrow and flipped. Okay, so that's just kind of investigating what does the number in front of absolute value do? And we can see some things that are happening. Now we're going to look at what does the number, what happens when I add or subtract numbers to this. And there's different things that happen if I add or subtract a term inside my absolute value versus adding or subtracting something outside of my absolute value. So now, go back into my Desmos, get rid of this -3. So now I have identical graphs here. And the first part of that second row is inside my absolute value subtracting 2. And so our green graph shows us the result of that. And we subtracted 2, and what it looks like happened is the entire graph moved +2. It moved 2 to the right on my graph. What if I subtracted 5? Moves over 5. Subtract 8, moves over 8 to the right. Kind of the opposite direction of maybe what you anticipated, right? If I look at the last graph in my investigation, it says, what if I add 2 instead of subtracting 2? Shifts to the left, okay? So it doesn't change how narrow or wide the graph is. The graph stays the same shape. It's just shifting right or left along the x-axis. So let's look at those 2 examples in our investigation. So again, let's draw in our first graph. So just go 1 over 1. Here's my initial function. Let's do the same in the last graph here. You hear my dog eating, eating her bowl of food in the background. It's very loud. On our first one, we observed that when we subtracted 2 inside my absolute value, I moved to the right 2. So my whole graph just shifted over, and now it started at 2 instead of starting at 0, 0. Started at 2, 0. And when we, instead of subtracting 2, when we add 2 inside my absolute value, we observed that the graph went to the left 2. Went to the left, over here it went to the right. And these transformations, we'll notice the further we get in algebra, that they're consistent with all sorts of functions, okay, on how things shift and move. So they're good observations to make as we add more types of functions to kind of our toolkit. So last, let's look at what the effect is when we add or subtract a number outside my absolute value. So before going back to Desmos, let's draw in our, what we call a parent function, okay, the function we're always comparing it to, which is just y equals the absolute value of x. Okay, so there's my original graph. Let's make both of these the same. Okay, so I have y equals the absolute value of x. And if I subtract 2 now outside the absolute value, there goes my graph down 2 units. If I subtract 5, down 5 units. If I add 3, it shifts it up 3 units. So what we've just observed is that adding or subtracting outside of that absolute value moves my graph up or down. It's a vertical shift. Go back to my notes. So we observed that it went down 2. So from 0, 0, we went down to 0, -2. And then had the same graph in terms of shape, but it was shifted down 2. Okay. So our investigation kind of showed us what happened. We still want to think about these transformations while we're graphing, but I'm going to give you kind of a list of characteristics that should help you graph any function that you're given for absolute value. So our general form of an absolute value equation or absolute value function, okay, it is a function because every input only has one output, is y equals a absolute value of x subtract h plus k. So just like we have y equals mx plus b for our line, and we know that m is our slope and b is our y-intercept, and that's how we graph it. For our absolute value functions, we have y equals a, absolute value of x minus k plus x minus h plus k. Okay, we know things about h, k, and a that help us graph the absolute value in the same way that m and b help us graph a line. Okay, so one thing that we observed about a, okay, so let me kind of color code here which goes to which. So we're going to talk about 3 things that a helps us determine. One thing that a helps us determine is whether the graph opens up or down. So when we saw in our investigation, when the number in front of absolute value was positive, my graph was opening up. Once the number in front of the absolute value became negative, my graph opened down. So one thing that a tells us is if a is positive, then my graph opens up. So V-shaped graph opening up like that. If a is negative, then we know it opens down. My graph will look like that. Okay. The other thing that we saw a doing, if we go back up to our investigation, is if a was a fraction that was less than 1, it gave me a wider graph. And if a was a number greater than 1, then it became a much more narrow graph. Okay. So if a is greater than 1, so for example, our graph up above, y equals 3 absolute value of x, then the graph becomes more narrow. If a is a fraction, but more specifically, if a is greater than 0, less than 1, okay, so it doesn't have to be a fraction. I guess it could be a decimal as well. Okay, so some value that's between 0 and 1, but does not equal 1. Okay, for example, up above, we looked at y equals 1/3, absolute value of x. We saw that that made our graph get wider. The last piece with a, which I kind of briefly talked to when I was graphing, is that we can kind of use a like slope or the rate of change that's happening to get the shape of the graph. So when a was 3, I went up 3 over 1 to get the narrow graph. The thing is, it's not exactly like slope because over here, I'm actually going -3 if I think about it like a line and think about it like slope, right? So that a value is my rate of change. And what happens, that's on the right side of the graph. And what happens is it's symmetrical over that. It's flipping over. But we can kind of use A, okay, like slope. So AX like slope, where we can talk about rise over run. And we go to the right and then use symmetry to get V shape. Okay, so we can use that rise over run, get the right half of my V, and then just mimic it, use symmetry to get the other side. Then we also have these values H and K. What H and K do is, that's this, right? Shifting inside and shifting outside, which made it go right, left, or up, down. What they're actually moving is our vertex point. It moved the vertex to the right 2. It moved the vertex down 2. And so my vertex point means where the V meets. This is my vertex point. Okay, and so anything that I add, subtract, whether inside or outside my absolute value, is shifting that middle point of that V, that vertex point. Okay, and so HK, and I like to say the opposite of HK, and we'll talk about that in a minute, is the vertex of the graph, meaning here's my graph. The point where it meets is the vertex. Now, the reason that I say opposite of H is because it's set up as X minus H. So I'm going to give us a few examples of why I'm saying opposite H. If I have X plus 2, if I were to rewrite that so it matches X minus H, then I would write X minus negative 2, because a double negative is a positive. So if I write it absolutely true where I keep the X minus, then if it presented itself like this, I'd have to rewrite it as X minus negative 2, and it would still be X plus 2. That's because my general formula is written this way. And that's also why when we added 2 up above, we actually went to the left 2. Okay, because it is the opposite of what you may what you may think. When I add 2, I actually go backwards 2, but that's because of this setup where it's actually X subtract H in my general formula. When I add 2, that's subtracting negative 2. I'm going negative 2 to the left. If it was just, for example, X minus 4, that's still keeping X minus, and then I have 4, so it's positive 4 to the right that I would move. Okay, so that's why I say opposite of H. Instead of thinking about kind of this too much, we can always think about that it's the opposite of kind of how it presents itself. So when I add 2, I'm actually going negative 2. When I subtract 4, I'm actually going positive 4 to the right. And that's because of our kind of basic formula set up here. So let's use this to graph, and I think it'll become quite a bit clearer when we graph one of these. And I actually think these are quick and fairly easy graphs, okay? So when we graph absolute value, we're going to identify A and HK, okay? So before we do anything, we're gonna say, what's my A value? And then we'll write a little bit about what that means. And what's my vertex point? What is H? What is K? And so I'm going to rewrite my general formula here. Okay, there's my absolute value formula. A here, that's that ninja 1. A is negative 1. That means, by the way, that it opens down because it's negative. So I know my graph should look like this. Okay, that it should be opening down. It's a negative A value. HK, and remember we take opposite of what's presented to us for HK. So when it's X plus 2, H is actually negative 2 there because that's X minus negative 2. Okay, that's what H is, negative 2. And K, it's just plus K. So whatever K is, that's what we take. It's K is 3. Okay. Now we will plot the vertex. So our vertex is -2, 3. -2, 1, 2, 3. And we will use A to get points to the right of that vertex. So A is -1. I'm going to go -1 over 1. And then I can use symmetry to get additional points and to create the V shape that the graph is. Okay, so here's my vertex. I know that it should look like this from there. A helps me know I go -1 over 1, and then using symmetry, you know, I also have a point here. And then I have an arrow on both sides extending past those points. It's not just like a little triangle of points here. It's still extending past arrows on both sides. There's my absolute value graph. Okay, and so you can see what happened here. The negative flipped it over. Then adding 2 made it go to the left 2. Adding 3 outside of my absolute value made it go up 3. In terms of what's happening transformation-wise, that's how I land here. Okay. So notice it gives some hints here. It says, where's the vertex? Does it open up or down? Graph one other point and then use symmetry. Okay, those are the steps we just went through. So here, again, I'm going to identify my vertex. I'm also going to talk about A, and then I'll make my graph. They're pretty quick once we get that information out. So A here would be 6. My vertex is at, so X subtracts 7, opposite here. So I'm just taking the H is 7. There's no K here. That just means K is 0. So my vertex is at 7, 0. A is 6, which means it opens up because A is positive, and it's going to be narrow because it's such a large number. So remember, larger it gets, the more narrow it becomes. If it was a fraction, more wider that graph would become. So A is 6 means I'm going to go up 6 over 1, and then I'm going to use symmetry. So symmetry around the vertex. So there's the middle of my V. Use symmetry to get another point on the other side. Oops. There's my V-shaped graph. Kind of looks like an animal, right? Like here's eyes and a nose, some ears. Okay, making sure we draw that line through those points with arrows on both sides. On our next example, A is -2, which tells me it's going to open down and it's going to be a little more narrow because it's greater than 1. HK, in this one, there is no value inside the absolute value with X, so H is 0. K is 9, meaning I'm going 0, 9 for my vertex. I think that's all the way at the top here, yeah. And get another point using A, so go -2 over 1, and then symmetry around the vertex gives me a third point. Drawing my each side of my V-shaped graph. Okay, let's look at a couple of more together, and I'll let you try some on your own. Why don't I just go ahead and do the first 3, and I'll let you do the next 3. So on our next one, got a lot going on here. So A is 1/2. It will open up and it'll be wider because it's a number less than 1. My vertex, HK, is at opposite of H, -2. K is -5/2. So I'm going to plot my vertex at -2, -5/2. That would be like -2.5. So I'm going to go -2, -2.5. There's my vertex right there. It's kind of like floating in between -2 and 3 on the Y. Okay. My A value is 1/2. So I'm going to go from here up 1 over 2, and I'm going to be kind of in the middle of that box. And then using symmetry, right? So there's the middle of my graph. There's my vertex. Using symmetry, I know I also have a point here. It's a little bit wider. There's my absolute value equation with a vertex at -2, -5/2, a value of 1/2. On our next graph, a is -2, negative, so I know it opens down. I also know that this will be more narrow because it's greater than 1. My vertex, opposite of h, so -9, 3. -9, 3. I think that goes to 9. 3, 3, 6. It does not go to 9. Hold on. 1, 3, 6, 7, 8, 9. I should have been there. Sorry. Okay, so this goes +9 to -9. I made assumptions I shouldn't have made. -9, 3. Going down -2/1 to get my first point, using symmetry to get the third point. Draw that in. So just like a line, I need 2 points to draw a line. I need 3 points to draw this absolute value equation on my graph. On our third graph here, a is -1. So I know that my graph will open down and it won't be narrower or wider than my parent function because it is 1. So it should be the same size as that parent function in terms of narrow wideness. HK would be +8, 1. So +8, 3, +8, 1. There's the middle of my graph, my vertex point. Going down -1, 1, using symmetry to get the third point. There's my graph, okay? So now I'm going to have you try the remaining 3 examples. Write HK, and your A value, what that A value means in terms of how it's affecting your graph, and then graph your function and see how you do. So let's just see how you did. My first graph should be opening down and be slightly wider using A as -1/2. HK is at -6, 0. Bottom graphs, this is down because it's negative, a little more narrow because it's greater than 1. My vertex is at 4, 2, going down narrow, V-shaped graph. This graph is going up because A is positive. It's going to be wider than my parent function, and my vertex is at -5, 1.